Have you ever heard someone say it's cold outside? In terms of science, this is a fictitious statement because there's no such thing as cold. Technically, it is more correct to say an object is lacking heat energy. You can only measure the amount of heat in an object, not the amount of cold in an object. Let's go through how to analyze the transfer of heat. Thermal energy stems from the friction generated between moving particles. Temperature is the measure of the average kinetic energy, or energy of movement, of particles. The higher the kinetic energy, the more heat generated. Think about how warm you get when you run around. Your muscles are stretching and contracting, generating friction, which makes you warmer. The second law of thermodynamics states that heat energy can only spontaneously flow from warmer objects to cooler objects. Imagine taking an ice cube out of the freezer and putting it on the counter. Since the counter contains more thermal energy than the ice cube, its energy moves into the ice cube. The flow of heat energy from the counter to the ice cube will continue until thermal equilibrium has been obtained. Thermal equilibrium is when all objects in a system are the same temperature. The amount of thermal energy an object possesses can be calculated. Here is the equation. Q equals mc delta T. Q is thermal energy in joules, J. M is the mass of the object in grams, G. C is the caloric requirement for the phase of matter the object is in, joule per gram degrees Celsius. For example, frozen water versus liquid water versus gaseous water. Delta T is the change in temperature, T final minus T initial. Look at this table showing the specific heat of various objects. These values tell us how much energy is required to raise 1 gram of the substance 1 degree Celsius. Notice water has 3 specific heat values for each phase water can exist, and 2 values with the term latent heat. Latent heat is essentially hidden heat. Water molecules get arranged in a crystal lattice structure when ice is formed. As thermal energy is added to ice at temperatures below zero, the energy warms the ice to 0 degrees Celsius. If more thermal energy is added, it goes into breaking apart the crystal structure of the ice, not into raising the ice temperature. A similar process occurs at 100 degrees Celsius. Water molecules stick together similarly to how opposite ends of magnets stick together. At 100 degrees Celsius, the thermal energy added to water goes into vibrating the molecules enough that they detach from each other and enter the gas phase. Since there is no temperature change in the vaporization process, the heat being added is called the latent heat of vaporization. Let's work on a problem involving energy transfer. When melting ice or vaporizing liquid, you use the equation we saw earlier without the change in temperature term. At phase changes, there is no temperature change. Q equals mc. Let's go through an example. 150 grams of frozen water is at negative 20 degrees Celsius. How much heat energy will it take to get the water's temperature to 50 degrees Celsius? The first step in this type of problem is to make an outline of stages the water goes through from its initial temperature to its final temperature. Stage 1. Heat ice from negative 20 degrees Celsius to 0 degrees Celsius. Stage 2. Melt ice. Stage 3. Heat liquid water from 0 degrees Celsius to 50 degrees Celsius. Now we can use the appropriate equation for each step to solve for the heat energy required at each step. After we have all these values, we add them together. Step 1. Raise the ice temperature to 0 degrees Celsius. Q sub 1 equals mc delta T. Q sub 1 equals 150 grams multiplied by 2.1 joule per gram degree Celsius multiplied by 0 degrees Celsius minus negative 20 degrees Celsius. Q sub 1 equals 6,300 joules. Step 2. Melt the ice. Q sub 2 equals mc. Q sub 2 equals 150 grams multiplied by 334 joule per grams. Q sub 2 equals 50,100 joules. Step 3. Raise the liquid water from 0 degrees Celsius to 50 degrees Celsius. Q sub 3 equals mc delta T. Q sub 3 equals 150 grams multiplied by 4.19 joule per gram degree Celsius multiplied by 50 degrees Celsius minus 0 degrees Celsius. Q sub 3 equals 31,425 joules. Q total equals Q sub 1 plus Q sub 2 plus Q sub 3. Q total equals 6,300 joules plus 50,100 joules plus 31,425 joules. Q total equals 87,825 joules. Notice that the total heat is positive. If we were to put that same amount of water as a liquid into the freezer, the total amount of heat energy would be the same to turn the water to ice, except it would be a negative value. To recap, thermal energy stems from the friction generated between moving particles. Temperature is the measure of the average kinetic energy of particles. The second law of thermodynamics states that heat energy can only spontaneously flow from warmer objects to cooler objects. Heat energy will continue to flow until thermal equilibrium is reached, which is when all objects in the system are the same temperature. Each substance has a caloric requirement, C. It is defined as the amount of energy required to heat 1 gram of the substance 1 degree Celsius. When water changes phases from solid to liquid, and from liquid to vapor, the heat added doesn't raise the temperature of the water. This is called latent heat. When melting ice, the heat energy breaks the crystal structure of the ice. When vaporizing liquid water, the heat energy separates the water molecules.